model and then develop the equation, or you can do it directly as well. Now, at the end of the last lecture, what we did was we looked at the t-test. So how to perform the t-test? The t-test is mainly to check if the mean value of a variable is close to our proposed value. So I showed you this data. This data has 12 values. So what is the chance of the mean of these 12 values to be close to 1800? Okay, so first of all, you find out the mean or the standard deviation of the data. Then you calculate the t-statistic, which is calculated like this, and then you find out, go to the t-table and find out the probability of t. Okay, which is the probability. So you need to find out how many degrees of variations you have, how many degrees of freedom you have, which is number of values minus 1, and your error value, how much error you are incorporating in the, or you are willing to accept in the observations, which is normally 5% on each side, plus or minus 5%. So 2.5% on each side. Okay, 5% total error. So 2.5% on each side. So you go to the table, find out the value of t for, if you have 12 values, then degrees of freedom will be 11, and 2.5% error is this value. So 2.20 or 2.19 they have taken in the book. So little bit of approximation doesn't cause a lot of difference in the values. Okay, so 2.20, 2.19 means the same thing. So your t value, which you calculated, the t statistic was less than the t from the table. That means there's a high chance that the mean of this data is close to 1800, or there is insignificant difference between the mean of the data and the required value, which is 1800. Okay, if the t statistic is more than the t statistic from the table, that means there is significant difference between the required value and the mean value of the data. Now this is the t-test, which we perform usually to test one variable. Okay, so you can see 12 values are given for the same variable, saturation flow rate. Now there is another test which is performed to find out the efficacy of the model itself. So in a model we have many variables, okay, many x values. So if you can perform t-test for each variable, taking one variable at a time. Okay, so it will tell you whether the model is affected by each variable or not. Okay, so for example, in a model you have age and you have income and you have number of cars, 3 inputs, and the output is, for example, number of trips. Okay, so you can perform t-test on each of these variables one at a time. Okay, so one t-test for age, one for income, one for number of cars. Okay, so it can be performed one at a time. Okay, but you want to apply a test which can tell you if the complete model is significantly affecting the output or not. Then in that case we perform the F test. Okay, F is the short form for Fisher test. Okay, so when I say F test, basically we are calculating a statistic, a number or a variable which is known as Fisher statistic. Okay, so Fisher's statistic is used for finding out if the complete model with all the variables has a significant effect on the output or not. Okay, so again we need a null hypothesis. Null hypothesis is always that beta equals to 0. Now this is the beta for all variables, not one variable. This is complete beta for all the variables. Okay, so the coefficient of x1 and x2 and x3, all of them complete. This is one vector, so beta is basically a vector here. Okay, so the complete beta of the model is 0 or not 0. Null hypothesis it is 0, alternate hypothesis is it is not 0. So if it comes out to be 0, if you prove the null hypothesis, that means the model does not have a significant effect on the output. If you prove that beta bar is not equal to 0, that means you are proving that model has a significant effect on the output variable. Okay, how to calculate the F statistic? The F statistic is calculated in this manner. Okay, so you can see some terms here. N means the number of values in the data set. Capital N means the number of values in the data set. Okay. J means the number of parameters you have calculated for the model, the number of inputs which you have. Okay, the number of inputs which you have, that is J. So if your model has 3 inputs, then J will be 3. Okay. What is RSS? RSS stands for residual sum of squares. RSS stands for residual sum of squares. And residual sum of square equals to TSS minus ESS. What is TSS? Total sum of squares. What is ESS? Error sum of squares. Total and error. Okay. And the equation for TSS and SSS is given here. Okay, we have already discussed it. We have seen it. Where is it? Okay, so TSS is this one. Okay, and TSS minus ESS, which is residual sum of square, equals to this one. Okay, so this is RSS directly, and this is TSS. Okay, so TSS is y minus y bar square summation. Okay, what is yi? Each value, single value of the data, and y bar means the mean value of the data. Okay, and y cap, this one, y cap means the value which you are getting from the model, and y bar means again the average value of the variable, average value of the output. So y refers to the output. Okay, so all these are for the output variables. So if your output is number of trips, then average number of trips will be y bar, and number of trips in different days will be y. Okay, y cap, number of days, number of trips predicted by the model, and y bar again mean number of days. Okay, so this is RSS. Okay, and this is TSS. Okay, for ESS, I'm not sure if I wrote the equation in the slides. Is it there? No, but you can see the equation number is mentioned. If you go to the book, you can find the equation there. Okay, 13.4.11, 30.4.12. Okay, let us see if I need it in the other in some question. I may show you the equation. Okay, so this is the F statistic for the model. Okay, first of all, calculate this F statistic for the model. Okay, then we have an F table. Okay, I'll show you the F table, and you can find it in any statistics book. You can find out the value of F from the from Excel as well. And if you search online, you can easily find the table for F statistics as well. Okay, so the statistic which you have calculated for the model, if it is more than the F, the standard F. Okay, the standard F means the F which you will take from the table, or from the from the table, F table, or from Excel, or from wherever. The standard F value, if you compare it, okay, and your F value, the standard F value, is less than the F value which you are getting from the model, the statistic which you are getting from the model, it means you will reject null hypothesis. Okay, beta is not equal to 0. That means beta is not equal to 0. Null hypothesis was beta is equal to 0. So when your statistic is more than the standard F value, that means beta is, give me a second. That means the beta is not equal to 0. Okay, so beta not equal to 0 means the model has a significant impact on the output. Okay, or in other words, the model is able to capture the significant portion of the trend of the output. Okay, whatever the trend of the output variable is number of trips or number of cars or whatever, okay, income, age, whatever the output variable is, the model is able to capture significant variation in that of the output. The actual variation of the output is captured by a large amount by the model. So whatever the model is giving is more or less as per the trend of the actual output. Okay, so that means the model is valid. In simple words, it means the model is valid. So whenever you reject null hypothesis, that means the model is valid for calculating the output. If you have to accept null hypothesis, that means your statistics is less than the F standard F value. That means the model is invalid. You cannot use it. Whatever model you have tried to develop, that is not good enough to calculate the output. Okay, so your equation is not valid. Go and recheck the equation, recalculate the equation, and so on and so forth. Now, for the standard F value, you need 2 degrees of freedom. So in T statistic, in calculating T statistic, I only needed 1 degree of freedom. Okay, that was the number of values. In calculating the F statistic or getting the F statistic from the table, I need 2 degrees of freedom. Okay, so one is J, which is the number of parameters you have estimated, the number of inputs, and the other one is N, which is the number of values in the data set. Oh, sorry, the other one is N minus J minus 1. Okay, and N is the number of values in the data set. Okay, and then you will calculate F value for 1 minus alpha, the probability of 1 minus alpha. So this is again the amount of error you are accepting in the model. The amount of error you are accepting in the model. So if I go back, yeah, 1 minus alpha is the level of statistical confidence. Okay, so 1 minus alpha basically means that for if you are accepting 5% error, then 1 minus alpha will be 95%. So you are 95% confident about your result. Okay, now you will see in most of the parameters, in most of the cases, we are taking alpha as 5%. That is normally the standard value. Okay, the standard value of alpha is normally 5%. So the error which we are willing to accept is normally 5%. 5% total. 5% total. So it can be 2.5% plus, 2.5% minus. Okay, and obviously it depends upon the type of table you are looking at. So 1 minus alpha, then it will be 95%. Okay, so if alpha is the amount of error you are accepting, then 1 minus alpha will be the confidence you have on in your values. Okay, so if you are accepting 5% error, 1 minus alpha will be 95%. Okay, now let me show you. Okay, let us look at an example, and I will show you the F table then. Okay. Not from here, it's not given in the book, although they are mentioning it, but it's not given in the book. Okay, so I will show you from Excel and I will show you our table online. Okay, but it doesn't matter, right? From wherever you get the value, doesn't matter. These values are fixed. Okay, multiple linear regression was estimated on a computer with the aid of a statistical package. The output includes, so this is error sum of square, they already calculated it for us, 45. This is total sum of square, 95.8. Number of values in the data set, 1220. So there were 1220 values available from which they made this equation. Number of parameters estimated is 8. Okay. Check whether the equality of all dependent parameters estimates to 0. Okay, or can be rejected with 95% confidence, statistical confidence. Okay. So again, 95% statistical confidence means 5% error. Okay, and this is the null hypothesis. Null hypothesis is all dependent variable parameter estimates to 0. Okay, which is basically beta bar. Okay, so that is the parameter estimate for all dependent variables. Okay, beta bar. Okay, so we are given with error sum of square, total sum of square, and FSS is calculated in this manner. So RSS equals TSS minus ESS. Okay, RSS, residual sum of square, means total sum of square minus error sum of square. So both these values are given. Okay, so here you see For RSS, I'm doing TSS minus ESS. Divide by 8. 8 the number of parameters, the input parameters. Okay. Then divide by error sum of square, divide by n minus j minus 1, which is this value. Okay. And this whole ratio comes out to 171. 171. Okay. Now I will compare it with a standard F value. Okay. For standard F value, again, I need 2 degrees of freedoms and I need the confidence interval, the confidence level. Confidence level already given 95%. Okay. Sorry, yeah, 95%. And the first degree of freedom is the number of parameters you are calculating, j value, which is 8. And the second degree of freedom is n minus j minus 1. Okay, n minus j minus 1. So n is 1220 minus j, which is 8 minus 1. So 1220 minus 8 will give you 1212 minus 1, 1211. Okay. Now how to take the value of f? Let me start with Excel. Okay, so the function is f distribution. Okay, let me. Okay, the function which we are using is f distribution. Okay, so you can see the explanation is given here. Returns a right-tailed f probability distribution. Okay, degree of diversity for 2 different sets and so on and so forth. Okay, so f distribution. If you select it, it will ask you the value. Okay, I think this is to get the the probability then. Yeah, f inverse. Okay, f inverse. So first of all, you will put here the value. The function is f inverse f dot inv. Then you open the bracket. In the bracket, then you would put the value of the probability. Okay, the the 1 minus alpha value, which is 95% for us. Okay, then the degrees of freedom, 2 degrees of freedom, we have 8, and then we have 12, 11. I think the probability should be in this value. Okay. Okay, so the probability should be in fraction. Okay, and then you have this. Okay, and then you compare it with the value you got. Okay, 1.94 is a standard F value. The value which you have taken from the Excel sheet is the standard F value. Okay, and then you compare it with the statistic which you have calculated for your model, which is 171. Now 171 is way more than the standard F value. Okay, so if the statistic is more than the standard F value, what does it mean? Let me go back. What would you say if the statistic, so this value is more than the F value from the Excel, what would you say? What is your decision then? What does it show? What does it show? If the statistic is more than the standard F value, what does it mean? Tell me. Anyone? I just told you. It's written that if this happens, then you will reject H naught. You will reject that beta bar is equal to 0. So beta bar is not equal to 0. What does it mean? What does it mean for the model? I'm trying to test the model. What if beta bar is not equal to 0? What does it say about the model? Anyone? No one? Okay. Let me tell you again. It, in simple words, it means that your model is capturing, or sorry, your model is valid for predicting the output. The equation which you have developed is valid, is good enough to calculate the output which you wanted from the equation. So if you develop the equation to predict the number of trips per day, then if this happens, if you are rejecting H naught, then that means the model is good enough to predict the number of trips per day. Okay, if this doesn't happen, that means the model is not good enough to predict the number of trips per day. If you are calculating number of trips per day from the equation, that means you can do that only if this statistic was more than the standard F value, okay, which it is in this case. So for whichever equation these values were given, that equation is good enough to calculate the output. Otherwise, it will not be considered good. Okay. So this tells you about the goodness of the model. Okay. This is a term which they use, goodness of the model. Okay. Yeah. Now, in some cases, so for example, you are trying to develop a model which will give you number of trips, okay, number of, or flow, okay, a flow, or let's say what example they are giving, automobile ownership, okay, number of cars owned by a household. For example, you are trying to develop a model, an equation which will predict the number of cars in a household, in a particular household, okay. Now, obviously, you are developing the model for everybody living in your area, right? Okay. Now, people living in your area may be of different types. Okay. So some of the people may belong to middle income category. Some of the people may belong to lower income category, and some of the people may belong to higher income category, right? So, obviously, people who belong to lower income category, number of cars owned by them will be more or less. Tell me. Number of cars owned by lower income category will be more or less. Tell me. Yes. What is the relationship between number of cars
Doctor,
and
I couldn't hear you very well. Number of cars, where exactly?
number of cars owned by a lower income household will it be more or less?
Less.
Less. Okay.
Yeah,
So
sure.
yeah. So if you can make three different segments in your, you can divide your data. So you have the data for the entire area, all the households. Okay. If you can divide the data into these three categories, okay, higher income, lower income, and middle income, and then you develop a model for each one of these categories separately. So there's an equation to predict number of cars for higher income people, equation to predict number of cars for low income people, and equation to predict number of cars for middle income people. Okay, then your model will be simplified. There will be less variation in the model. Okay, because variation is mainly caused by the income. So you are distributing the model, you are having a different equation for each income group. So the equation will be more accurate, okay, because there will be less variation in the data set for which it is developed. Okay, another example which they are giving is the flow characteristics. Okay, so for example, you are predicting travel time, okay, and you have some 2-lane highways, some 4-lane highways, and some 6-lane highways. Okay, now what do you think the travel time for which of these highways will be higher? Which of these highways will have the highest travel time? 2, 4, or 6? Tell me.
2, doctor.
Yeah, 2-lane highway will have the highest, and the other one will have lower and lower. Okay, so if I can make three different equations instead of making one equation, which I'm applying to 2-lane highways and 4-lane highways and 3-lane highways, I can make three different equations. One equation for predicting travel time on 2-lane highways, one for 4-lane highways, one for 6-lane highways. What will happen in that case? My equations will be more accurate and they will be simplified. Okay, so in certain cases, it is more convenient, more efficient, and it will yield you more accurate results if you divide your population, your data set into categories, and you develop a different model for each category. Like I have given you just two examples. Categories of different types of highways, or categories of different types of households. Okay, another example can be the one which is more familiar to us, the categories of highways on the basis of their function, local road and arterials and collectors. If you develop different functions or different models for each of the type of highway, then those models may be more accurate and simplified as compared to one equation which is covering all of them. Okay, so in certain cases we like to segment our data. Segmenting means we like to separate our data into different categories. Okay, so we have a combined data set, and then we divide that data set into 2 or 3 different categories, and then we develop an equation for each of these categories, like I have given you the examples. Okay, so 3 examples given. We have to discuss 2. Another example is trip characteristics of people on the basis of gender. Okay, so for example, number of trips taken by one person in a day, and you are trying to develop an equation to predict that. Okay, so either you can develop a single equation for all types of travelers, or you can, if you feel that trip characteristics are dependent upon gender, then maybe develop one equation for male travelers and one equation for female travelers. Okay, and this does happen. Okay, there's no racism or discrimination in that in many countries trip characteristics are dependent upon gender. Okay, this is a fact, we cannot change it. So those 2 equations, one for male and one for female, may be more accurate and simplified as compared to the single equation which will develop for both of them combined. Okay, so that's why we sometimes need to do some segmenting in the data set. Okay, for car ownership, they are saying you may segment the data on the basis of urban and rural communities. So develop one equation for urban areas, another equation for rural areas, because in urban areas car ownership is usually higher, in rural areas it is lower, and people characteristics are also different in urban and rural areas. Okay, and so on and so forth. So these are some examples why segmenting may be important. Okay, but the main point here is we don't want a single equation for all the travelers which is less accurate and complicated. It is better for us if we have 2 or 3 or 4 equations which are more accurate and simplified than that single equation. Okay, so if you divide your data set into different categories, then you can develop one equation for each category, and since that equation is dealing with a data of less variation, then that equation will be simpler and it will be more accurate. Okay, now the problem can be, for example, you go to a country, for example, you go to Saudi Arabia, okay, or you go to USA, or you go to Pakistan, and there you have seen that they are developing different models for urban and rural areas. Okay, we have seen that there, and according to them, they are doing good. According to them, they tried these 2 different approaches, and they found that developing a separate model for urban and rural areas is good for them. Okay, now you come to Bahrain. Okay, you are somebody like me, somebody hired you here in Bahrain, and you are coming from Pakistan, you have experience of Saudi Arabia as well. You come there and you say, why don't I do the same thing for Bahrain? Why don't I develop a model which is separate for urban residents and rural area residents? Why don't I do that? Because in these 2 countries it was very successful. Okay, I'm just giving an example. Okay, I don't know what the actual situation there is, but you come from there and you say, fine, I will apply the same methodology here. Maybe for Bahrain population, this categorization is not valid. Okay, maybe there is no difference between the travel characteristics of urban areas and rural areas in Bahrain. Maybe. Okay, I'm not sure. Okay, so how to check that? Okay, so you may end up making 3 or 4 categories in your data set, and you develop 3 or 4 equations which were not required at all. Those equations may be giving you the same accuracy and same simplicity as a single equation for the entire data set, because the categorization which you are doing is not valid for this country. Okay, so like we discussed the gender categorization on the basis of gender. So maybe if Bahrain or Saudi Arabia or some other country applies gender classification, gender categorization on their data set, it is more convenient and more fruitful for them as compared to this categorization applied in Western countries. Okay, maybe their gender does not affect travel that much. Okay, so once you make the categorization, you have to make sure that separating the data on the basis of that variable was fruitful. Okay, it was advantageous. It has some advantages. Okay, we were not doing it unnecessarily. We did not do it unnecessarily. Okay, so there's a test for that as well. We call it the test of equality for segmented linear models. Okay, so what we are testing, should we divide the data into different sets and develop different equation for each set, or should we just take it combined? This is what we are testing. Okay, so our null hypothesis is that all models are giving the same results or they are giving different results. Okay, this is what we are testing. Okay, so this is first of all, you will create a pooled model. Pooled model means the model which is for the entire data set. The model which is for the entire data set without any categorization. Okay, so if you are doing categorization for male and female, you will develop a model without the categorization. So male, female, all of them are included in the same data set, and you develop one equation for them. Okay, so that is the pooled model. Okay, and then we have the segmented models. So for example, you divided the data into 2 categories, 2 segments, and then you develop the equation for each segment. So this is the equation for segment 1, the equation for segment 2. Okay, so the hypothesis which we are testing is that these coefficients beta 1, beta 1 1, beta 1 2, beta 2 1, beta 2 2, beta 2 3 1, beta 3 2, these coefficients are almost equal to each other. Okay, so if they are almost equal, then why should I have 2 equations? I can combine them into 1 equation. Okay, so this is what we are testing. Okay, that these coefficients which are in different equations, if they are almost equal to each other, then we should not segment the data into different sets. Just make one equation which is good for all. Okay, so this is a null hypothesis that coefficients are equal. The alternative hypothesis is none of the coefficients is equal. Okay, the statistic which you will calculate is this statistic, and again we will check it with the f value. The value from which you will check it is the f value. Okay, so ESS means error sum of square for the pooled data. Okay, so P is not multiplied here. Okay, keep it in mind. P means this is for the pooled data, the complete data set, the equation which you develop for the complete data set. So error sum of square for the complete data set, error sum of square for the first segment equation, error sum of square for the second segment equation. Okay, then J means the number of parameters in the pooled data. Okay, J means the number of parameters you calculated in the pooled data. The number of inputs again, the number of inputs. Okay, then ESS 1 means error sum of square for segment 1 equation. ESS 2 means error sum of square for the second equation. N1 means number of values in the first segment. J1 means number of parameters calculated in this equation, number of inputs for this equation. N2 means number of values you had in segment 2, and J2 means number of inputs you had for this equation. Okay, and so you calculate the statistic, and again the rule is the same. If this statistic is more than the standard f value, then you will reject it. Then you will reject what? Null hypothesis. Okay, rejecting null hypothesis in this case means that having 2 equations is good, or having different equation for different segments is good, rather than having a single equation for the pooled data. Pooled means combined. Pooled means combined. Okay, So we have an equation for the combined data set, and we have then equations which are for each segment of the data. So we are testing, should we have a single combined equation or should we have multiple equations for each set of data? Okay, so if null hypothesis is rejected, meaning this ratio is more than the standard f value, then that means the null hypothesis is rejected. Null hypothesis rejected means having different equations for each set of data is good. Okay, keep it this way. If null hypothesis is accepted, meaning this ratio is less than the standard f value, that means you should have only one equation for the complete data set. Don't segment the data according to the category which you have selected. Okay. Now at this point, I may add that it may happen that there are different possibilities to segment the data. For example, you can segment the data according to location. Okay, for example, rural areas, urban areas, or you can segment the data according to gender, male, female. Okay, so whatever segmentation you have applied, you will apply one of them at a time. Okay, you will apply one of them at a time. So either you segment the data according to population, or sorry, location, or you segment the data according to gender, and then you will check if this segmentation was valid or not. Okay, by doing this test. So you did the segmentation and you found that this ratio is more than the standard f value. That means the segmentation is good. You stop there and you have different equations for each segment of the data. Okay, so for example, you did the segmentation for urban and rural areas and you found the test to be true. The ratio was more than the standard f value. So on the basis of gender, I can separate the data. But let's say you separated the data on the basis of gender, and this test proved that your segmentation was not good. Okay, the ratio comes out to be less than the standard f value. That means what? That means the segmentation according to gender is not possible. Some other segmentation may still be possible. Okay, so you develop one equation for male, one for female. You did this test. The ratio was less than the standard f value, so I should not have different equations for each gender. Okay, but maybe I can have different equations for each location. Okay, then I can try developing a different equation for urban areas, rural areas, and repeat the same process to find out if this segmentation is valid or not. Okay, it can happen that in one data set, multiple types of segmentations are possible. Okay, so you need to keep it in mind. Okay, so for a particular data set, they have given us these statistics. Okay, so obviously if you try to do what we have done in the last lecture and what we are doing new here, one example will take the whole class. So that's why they are giving us examples and problems in portions. Okay, so they are just telling us do this part at a time. That's it. Okay. The following summary statistics are given for pooled and segmented data for linear model, and we need to find out if the segmentation, the equality of parameter for segmented models. Okay, can we have different data? Can we have different equations for the segments, or should we have one equation with a pooled data set? Okay. So we need to calculate the statistics for each model. They have given us ESS and TSS. These are the only two things which are required here, ESS and TSS. Okay, how they are calculated, you can go back and look at the equations. Okay, but we need the model for that. But here they are not giving us the model, they are just giving us the calculated statistics. So ESS and TSS for the pooled data set. In the pooled data set, there were 5 input variables and 645 values. These 645 values were divided into 2 segments. So segment 1 had 305 values and segment 2 has 340 values. So if you add them, you should be getting 645 again. Okay. ESS and TSS again given for each equation of each segment, and the number of parameters, the number of input variables are the same, 5 and 5. Okay. Now we need to calculate the statistic for this for this scenario. So it was ESS for the pool data, which is 180, minus the ESS for each segment. So 60 plus 73. Divide by what? J plus 1. Okay. Number of parameters for the pool data plus 1. So number of parameters is 5 plus 1 is 6. Okay. Divided by ESS again for segment 1 and segment 2 data. Divide by 633. How did I get 633? It was 645. Okay. And then sorry. So N1, which is 305, number of values in segment 1, minus J1, number of parameters for segment 1, that is 5. So 305 minus 5 minus 1. Okay. Plus N2, number of values in segment 2, which is 340, minus number of parameters in segment 2, which is 5 again. So 340 minus 5 and then minus 1. Okay. So if you add both the brackets, you will get 633 in this case. Okay. So if you calculate the total ratio, it comes out to be 37.3. And if you check it with the standard F value, now standard F value, again the probability is the statistical significance you want is 95%. So my alpha is the error which I'm applying is 5%. So 1 minus alpha is 95%. Okay. Degrees of freedom, J plus 1. J is 5 plus 1. Okay. And second degree of freedom was this number. Okay. An easier way to remember is whatever you are dividing in the numerator will be the first degree of freedom. Whatever you are dividing in the denominator will be the second degree of freedom for the F value. Okay. So 6 and 633. Okay. Now let me go back to Excel again. And again, I will use the same function. So I will just change the values. This one is 6 now. And this one is 633. Okay, so 2.11. 2.10 Excel obviously is more accurate, and maybe they are doing some approximation, but plus minus 0.01 here and there doesn't make much of a difference. So you can see the statistics is way above the standard F value. The statistic which you have calculated is way above the standard F value. So what is my decision now? Should I have two equations, one for each segment, or should I have one single equation for the pooled data? Tell me. If the ratio is more than the standard F value, that means null hypothesis is rejected. H0 is rejected. So if H0 is rejected, what is my decision? Should I keep equation for each segment, or should I make one equation for the entire data set? Tell me. Anyone? What is your decision here? Should I have two equations, or should I have one equation? One equation means single equation for the entire data set. Two equation means one equation for each segment of the data. What should I have? This one or this one? Okay, whenever the null hypothesis is rejected, it means that there is significant difference between the parameters. Okay, so you should have you should keep the two equations for each segment of the data. Okay, you cannot combine, or if you combine, then the error will be higher. You should not try to combine the two data sets into a single pool data. So in this case, my answer would be have two equations, one for each segment of the data. Okay. Now, how do we judge what are the tests we perform to show that my model is having or my model is good? Okay, what are the tests which we perform, or how can we determine if the model which we are using is good enough for calculating a value? Okay, so for example, we have this model y equals this. Okay, where y means number of household automobiles, number of cars in a house, in a household. X1 is the number of drivers. X2 residential density, number of people living per unit of the area. X3 is the income per person, and X4 is the number of household workers, number of people in a household who are working, who are doing a job. Okay, so we have developed a model for y, and these are our values. Okay, the beta, these are the beta parameters. So first of all, you can find out the overall fitness of the model by calculating R square. Okay, what is R square? R square is the R square is the coefficient of determination. Okay, how to calculate the coefficient of determination? This is the equation. Okay, so if you calculate the coefficient of determination and it is more than 0.4, I think it was 0.4. Anyways, if you calculate the R square for the model, it is more than 0.4. That means the model is good enough. This is one indication that the model is good enough. Okay, so you can calculate R square for the model if you have the values. Obviously, in this case, the values are not there. Okay, you should have values of y. Okay, you should have values of y and x for each of the house. Okay, for each household, I should tell you how many cars are there and how many people are working and how many. So the values of x1, x2, x3, x4, you need it for each household to calculate the R square. Okay, but here the purpose is not to calculate the R square again because it will take a very long time. The purpose is to show you the process. Okay, so the first thing which you can calculate is R square for the model. If R square is more than 0.4, then you say the model is good enough. This is one indication that the model is good, having R square more than 0.4. Okay, then you can perform a t-test for each of the variables. You can perform a t-test for each of the variables for x1, x2, x3, and x4. Okay, we can perform a t-test for all these 4 variables. Okay, let me go through that. Well, this is for this we have the data set. Okay, now in this case, the t value, so you can see the parameter 0.71, and then you see the numbers. There are certain numbers which are given in brackets here. Okay, the numbers which are given in brackets are the standard deviation for this parameter for x1. So this is the standard deviation for x2. There is a standard deviation for x3. There is a standard deviation for x4. Okay, so t value is calculated as this coefficient divided by the standard deviation or standard error. Okay, you call it standard deviation and standard error, it means the same thing. Okay, so first of all, you will calculate t value for each of these parameters. Okay, so for example, if you want to calculate the t value for x1, it will be calculated as so t for 0.71 divided by 0.02. How much is that? How much is this? How much is this value? 0.71 or 0.02? How much is it?
3550.
3550.
Yep.
There is no decimal here, right?
No decimal.
Okay. Then so this is the t value. Okay. Now you check the t value from the table then. Okay. So for performing the t test. Okay, so we calculated this statistic, the t statistic. Now we will calculate the value from the table. For that, I need the degrees of freedom, which is number of values minus 1. I have 1400 values. 1400 minus 1 is 1399. Okay, and then I'm again using the same level of confidence, same error level. So this will remain 0.025. Okay, so if I come here 399 is not given the table. Okay, for 399 degrees of freedom, the value is not given the table. Okay, so because after 399, sorry, after 30, okay, the reason is that if the degrees of freedom are more than 30, okay, now my degrees of freedom are what? 1399. Okay, so obviously more than 30. In that case, for any degrees of freedom which is more than 30, the value of t equals to the last value on the column. Okay, so now if you have 31 or if you have 3100, it doesn't matter. If the degrees of freedom are more than 30, the value of t will be the last value in the column. So that last value is 1.96. If I make it approximate, this is 1.96. Okay, so I can come here and obviously this value is way above 1.96. Okay, now you can do the same thing for t for x2, and again now you will use 0.71 upon 0.03. Okay, if you do 0.7 upon 0.03, it will again be a very high number, right? It will be a very high number. Okay, and you are still comparing with the same number because your degrees of freedom are still 1399 and is still the same. So 1400 minus 1, 1399. So the t value will remain 1.96. Okay, so it doesn't matter. Okay, whatever number you will get from here, it will be more than 3000 and you are still comparing with 1.96. Okay, so you can calculate the number, but I can safely say that this number will also be more than 1.96. Sorry,
tx1 equal 35.5. I'm sorry.
okay, and what about this one?
This one 1 minute. This one 23.66.
Okay, so it's still same thing. Okay, you are still comparing with 1.96, so it is way above that value. Okay, you can do the same thing for x3 and x4 as well. Okay, you take the parameter, divide by the standard deviation of this parameter for x3.
23 is less than 30. It should be in the table.
Sorry,
23.6 less than 30.
no. Degrees of freedom is n minus 1. So n is 1400. Okay, we are not looking for this value in the table. This is not degrees of freedom. Okay, this is the t value which we will compare with the value coming from the table. Okay, so the value coming from the table is 1.96 and I'm comparing it with 35.5 here. Okay, so this is the value for comparison, not degrees of freedom. Degrees of freedom is n minus 1. How many values were there in the data set? N minus 1, 1399. Okay, so degrees of freedom is 1399. Okay, got it?
Yeah, got it, doctor.
Okay, so okay, so if you do it for x3 and x4 as well, you will still get the same. I think you will still get the same result. Okay, so 0.052 upon 0.013. Okay, again 0.013, right? Because you are dividing with a very small number, so obviously each time you will be getting a very high response. Okay, and then for x4 are doing 0.28, 0.05. What is this? The last one? Or you can tell me the third one. Just want to make sure. The third one. Sorry?
4.
For the third one, TX3?
Yeah.
4.
Yeah.
Now, what does it mean? What does it mean? Whenever the t value for each parameter, for any parameter, is more than the standard value from the table, that means that parameter has a significant effect on the model. Whenever the t value for the parameter is more than the standard t value from the table, that means the parameter has a significant effect on the model. That parameter should be kept in the model. Okay, so for a good model, the first condition is it should have a high r square, high meaning more than 0.4. The second condition is that for all the variables in the model, for all the x values in the model, the t value should be more than the t from the table. Okay, the statistic for each of the x parameters in the model should be more than the standard t value from the table. This is the second condition. Okay, then the third condition is the f test, which is for the complete model. The f test is for the complete model. Now, the statistic for the complete model, the f statistic, which we have discussed earlier. This one is already calculated. Okay, and which is given as 326. Okay, and now I can check it with the f value, the standard f value. Okay, so again I will go back to Excel. The probability remains the same. J is the number of sorry, how what is it? And j, yeah, so j is the number of parameters you have, which is 4, and n minus j minus 1, so n is 1400, j is 4 and minus 1, so 1400 minus 4 of 5, 1400 minus 4 minus 1 is 1395. Okay, so 2.37. The f value which you have for your model is 326. The statistic for your model which you have is 326. Okay, so obviously it is way higher than the standard value which you will get from the table. The value which I'm taking from the Excel is the standard f value. So your f value, the value for the model, the statistic for the model is more than the value which I got from Excel, the standard f value. So that means the model is valid to capture the trend of the data. The model is valid to capture the trend of the data. One more thing, r square value is given, which is 0.49. Okay, so the first condition is met because the value is given 0.49. Second condition, the t statistic, we perform the test for each of the t value, it is met. The third condition, that the f value should be more than the standard f value, again it is met. Okay, so we have done the first three conditions. The fourth condition is standard error of the dependent variable. Okay, the test, or not a test, it's not a test, it is basically you know, what can I say, it's a check. Okay, it's not a test, so we will not calculate any numbers. We'll not calculate any numbers. It's a check. Okay, now what is the check? The check is that the standard deviation of the dependent variable, the y. In this case, the y is number of cars in each household. The test is, or the check is, that standard deviation of y should be less than mean of y. Standard deviation of y should be less than mean of y. Okay, so like I said, if I give you the values of number of cars in each household, then you can calculate the standard deviation, and then you can calculate mean as well. And the check is that mean should be higher, standard deviation should be lower. Okay, so the standard deviation is already given here, 0.63. Okay, if they had given us the full data, we would have calculated mean value of y, and we could have checked that if it is more or less. Okay, but it is very simple. Check, calculate mean, calculate standard deviation, compare. Mean is higher, good. Mean is not higher, not good. Okay, now this particular check, condition number 4, that mean should be higher than a standard deviation for the dependent variable, for the y. This has nothing to do with the model itself. Okay, so for example, you calculate mean as standard deviation. Mean is less, standard deviation is more. It doesn't mean the model is incorrect. It means the data which you collected is incorrect. Okay. For normal data, for a data which is collected in normal circumstances, mean should be higher than standard deviation. So model is not valid. Why? Because the model was not developed correctly. It is not valid because the data which was used for developing the model was not correct. Okay. So if for the dependent variable mean is higher than standard deviation, it means that the data which was collected and which was used for developing the model is correct. It has no problem. But if mean is lower, standard deviation is higher, that means the data which was used for building the model was incorrect. Then you go back and you have to recollect the data. Okay. The fifth point is, now you look at the coefficients for each of the x values and you think whether it makes sense or not. You look at the value of the coefficient 0.71, 0.71, 0.052, 0.28, and you look at their sign. So the coefficient for x1 is positive, x2 is positive, x3 is positive, x4 is negative. Does it make sense? Okay, how do I check it? Now let us go through it, and it will clarify inshallah many concepts related to planning. Okay, so I am trying to calculate number of cars, right? First of all, let us check the sign. Are the signs correct? So for example, for x1 means what? Number of drivers in the household. It has a positive sign. That means what? If number of drivers increase, the number of cars in the household will increase. Do you agree or not? If number of drivers, number of people who have license, do you agree or not?
Yeah, agree.
Okay, good. X2, if residential density means population of the area, so you can see it can be either 1 or 0. It can be either 1 or 0. So if household is in low density location, it will be 1. If household is in high density location, it will be 0. Low density means suburban area, away from the commercial center, and 0 means close to the commercial center. Okay, so the model is saying that if someone is living in the suburban area, low density area, then the number of cars in the household will be more, and vice versa. Do you agree or not? If someone is living away from the center of the city, then they will have more cars than people who are living inside the city. Do you agree or not? Take a guess. Should it happen that number of people who are living away from the city should have more cars as compared to people who are living inside the city? Should it happen?
It could happen, doctor, because they need cars to go to the city, right?
Yes, exactly. Yeah, that's exactly the point. That if you are away from the city, then obviously you need a car. Okay, and this is, I can tell you from my experience. Believe me, I went to Pakistan when I went to Pakistan in summer, we were looking for a house. Okay, and I don't have a car in Pakistan because obviously if I keep a car, then who will drive it? So why should I keep a car for only 1 month? I go there for 1 month, maybe less than 1 month sometimes. Why should I keep a car there? Who will look after it? So I don't have a car there. So I thought about living or taking a house in an area which was outside the city. And I went there one time only. When I came back from there, I told my father and my wife, we cannot live there. Without a car, we cannot live there. Okay. Then we bought a house, alhamdulillah, in the center of the city. And we started living. And alhamdulillah, I don't even remember that I thought about buying a car at that time. Believe me. Okay. So this is from my personal experience. X3 is income per person. This is very simple, right? It has a positive sign. Okay, income increases, number of cars in the household will increase. I think it doesn't need any debate, right? More income, more number of cars. Okay, so I wish everybody should have 2 or 3 cars in their household, so you would have more income. Okay, x4 is negative. What is x4? number of household workers, okay, who commute to work by public transportation. Again, it's not a debate, right? If more people are going to work by public transportation, then number of cars in the household will be less. So that's why we have a negative sign, right? It has a negative sign, okay? So when this x4 increases, y decreases. So x4 means people who are willing to go by public transportation. So if more people are willing to go by public transportation, then y will be less. Number of cars required in the household will be less. So again, the last two are very simple and very obvious. Okay. Second, the last point, which is again related to point number 5. Okay, the last thing which you can check is the magnitude of the coefficient, the magnitude of the coefficient. Okay, so for example, you see the highest coefficient is for x1 and x2. It means what? X1 and x2 has more impact on y as compared to x3 and x4. Okay, it means that. Okay, so x1 is number of drivers in the household, x2 is the residential density, what type of area you are living in. Okay, so according to the model, both of them have equal impact. Okay, then the next variable which has impact on the model, higher impact on the model, x4, which is a number of household workers who are going by public transportation, and the least impact is because of income. The least impact. So I'm just talking about now the value. I'm not considering the sign now. I've already considered the sign, and all the signs are making sense to me. Okay, but now I'm talking about the values, the value of the coefficient itself without the sign. Okay, so according to the model, the parameter which has the least impact on y is income. Okay, location has more impact, number of people number of drivers has more impact, and number of people going by public transportation has more impact. Okay, now if you live in this area, the area for which this equation is developed, then you can tell me that the values are correct or not, the order of the values is correct or not. Should income have the least impact, or should some other thing have the least impact? Okay, so you check the sign and you check the values, and if they make sense to you, fine, model is correct. If they don't make sense to you, for example, income has a negative sign. For example, income variable has a negative sign. Does it make sense? No, it doesn't make sense. So that means there's a problem with the model. Okay, or maybe there's a problem with the data. I can go back, check my data. Did I collect the data correctly? Then I will come back, and if the data is correct, then I will recheck the process of building the model. How did I develop this model? Okay, so if any of these things doesn't make sense to you, you know the area, you know the trend of the households, and if these things don't make sense to you, that means either go check the data. If the data is correct, then you come back and you check the model itself. Okay, so these are the 5 points. Whenever you develop a model, you can check the model according to these 5 points. First of all, calculate r square. R square more than 0.4. Done. Move on. T statistic for each variable, for each parameter, and each of these values should be more than the value which you will get from the table, the standard T table. Okay, this is correct, fine. If this is not correct for any variable, drop that variable out. For example, you perform the check for x1, x2, x3, x4, the t test which we did. For x2, the t value was less than the t value from the table. So that means x2 should not be in the model. Okay, so you will redevelop the model without x2. Okay, this is what we have to do. If the t test, the t value for the variable is less than the standard t value from the table, then you drop that variable out and you will redevelop the model without that variable. Okay, then the next test was the f value test. Okay, and again the f value for the model, the ratio for the model should be more than the standard f value from Excel or from the table which you will get from the statistic book. And if this happens, that means the model is valid. If this doesn't happen, that means the model is not valid. So that means maybe the linear model is not good. Maybe you will go for some other model. Okay, or maybe there's a problem again with the data. Okay, the fourth test was regarding the dependent variable. Mean of the dependent variable should be more than the standard deviation of the dependent variable. Okay, why? So if this happens, check. If this doesn't happen, then you go back and you have to check the data collection then. This can only happen if the data is collected correctly. Okay, and the last thing was look at the sign of each coefficient in the model and look at the value of each coefficient in the model. The sign should make sense: positive, negative. Positive means with the variable y will increase, negative means with the variable y will decrease. Is it making sense? If yes, fine, go ahead. If it doesn't make sense, then you go back and revise the model or the data. Okay, and same thing with the coefficient values as well. So which coefficient is higher, it has more impact on y. The coefficient which is lower has less impact on y. Okay, so for doing this, you must have some knowledge about transportation planning and the travelers of that area. Okay, so now I'll stop here. If you have any questions, please go ahead, ask me. Otherwise, we will have a break for prayers. We meet after 15 minutes, inshallah. Any questions right now? Okay, let's meet after 15 minutes, inshallah. And remind me to restart the recording.